Alright, so moving on to problem 2 that was posted. The problem is set up that A plus B goes to C in reversible reaction in a CSTR, adiabatic, and then it gives you the following properties of the system. It says, clearly show each step of the CRE algorithm, which is the chemical reaction engineering algorithm. This is from, I believe it's from Fogler, except for evaluate for this scenario. Also show formulas for K and Kc as functions of t. Do not plug in values. So we're actually not going to, I mean, you can plug in values for fun if you want, but so this CRE algorithm, just as a review, or maybe, I don't know how much we went over this, but all it is one is your mole balance / design equation, two is your rate law, three is your stoichiometric table, and then four is combine, so putting it together for final equation, and then five is evaluate. Alright, so for this problem it says, we don't need to do this last step, evaluate. So to start with our mole balance on our design equation. So we have a CSTR. So if we do a material balance, we're going to get volume FA0 minus FA by the rate. And then this can be simplified to B equals our FA0 times our extent to disappearance by. So that would be our step 1. So step 2 would be the rate law. So for elementary reaction, we say negative RA equals R K CA CB, and then minus R K. K CC over KC. And this is because the KC equals KF over KR. So if you plug this in, this would be KR times CC. So this will be RA equals K CA CB minus CC over KC. Alright, so that's typically how it's written. So then for the next step, for part 3, do our stoichiometric table. So for this, we have in, out, and we have A, B, and C. So it says CA0 is for A, and so out will be CA0, 1 minus XA, use A as the basis. CA0 is given to be CB0, so we have CB0 that equals CA0. And then since the stoichiometry is 1-to-1 for A and B, we also have CA0 times 1 minus XA for this one. Because they're 1-to-1 and CV0 equals CA0. Otherwise, it would be CA0 times theta B times B over A X A. But in this case, B and A both equals 1, theta B equals 1. So that's how you get that. Alright, so for C, C0 equals 0, and so for out it would be CA0 times X, XA. Okay. So, now we can plug this into our rate equation. So, our rate equation would be, I'm just going to use X instead of XA at this point. So, K, CA is CA0 times 1 minus XA times CA0, 1 minus XA. That would be minus CA0 XA. Oh, if I said it, well, I'll just leave it over this KC. Alright, we have our rate equation. I guess I should have said this is starting step 4, combining. So we combined it in our rate equation, so now we can plug our rate equation into our design equation. Should remember our design equation was V FA0 X CXA. So now we have RA, so V equals FA0 XA divided by A CA0 squared 1 minus XA squared minus CA0 XA KC. Alright, and so that we could take a CA0 out, do that. So we'll say V equals FA0 XA divided by K CA0 CA0 minus XA squared minus XA KC. Alright. And so the next part would be normally to evaluate. So plug in the values given and evaluate, but we're skipping that step. It's just a matter of plugging in numbers, so nothing too important there. And so then the last part of the problem, it said also show the formulas for K and KC as functions of T. So for those, our K equals K at 300 Kelvin, exponent, our activation energy, over rate constant 1 over 300, that's 1 over T. And then similarly for the equilibrium, rate constant, is Kc at 300 Kelvin times e to the exponent, our reaction, the rate or gas constant, 1 over 300, that's 1 over 2. And so that's pretty much all I wanted for that problem. And so hopefully, there's, yeah, so the only, caveat is if we're plugging in actual numbers for different temperatures, you evaluate these expressions at the different temperatures, plug into your design equation. And so that's that. So yeah. Yeah, so just email me with any questions you guys have, and go over more stuff. I'll plan on doing more problems with like series and parallel reactions, because I'm assuming you want some examples of that. If there's not examples posted for like old exams. All right, thanks.